people are looking to the brain to take more inspiration about how to build and train these networks. And so they may morph over time into something that actually does match the brain in more detailed ways in terms of the structure of these artificial units and what they're capable of and how they connect with each other. So yeah, I mean, in some sense, the human brain does what it does via a connection of neurons. So in theory, we should be able to mimic that with a connection of artificial neurons. But what the really important bits are yet to be worked out.
Artificial intelligence is all the hype, and there are a lot of dystopian ideas surrounding it, ranging from putting us out of our jobs to enslaving, replacing, and destroying humanity. Most of this is based on the idea that artificial intelligence will be human-like, and that because of its intelligence it will automatically be conscious, and that a conscious machine would have emotions and similar desires as a human. In combination with the idea of exponential expansion of AI due to self-optimization effects when AI is used to make better AI, that could be pretty dangerous. But there are also a lot of assumptions here. So several scenarios are being discussed in books such as Life 3.0, Being Human in the Age of Artificial Intelligence by Max Tegmark, which I was gifted by my family and which I read with quite some interest. There were several scenarios that, according to Tegmark, could lead to human-like AI, or AGI, Artificial General Intelligence, which I, from the perspective of a neuroscientist, find to be placed solidly in the realm of science fiction. This is why I want to talk about artificial intelligence from the perspective of neuroscience in this episode. I want to thank my supporters on Patreon, who are very kind to stick with it during the turbulences and delays the podcast is currently experiencing. I am your host, Dennis Eckmeyer, and this is episode 53 of Science for Societal Progress.
I'm Grace Lindsay. I'm a postdoc at University College London at the Gatsby Computational Neuroscience Unit and Sainsbury Wellcome Center.
And what do you do?
I build computational models of the visual system, mostly, and try to relate them back to data from the visual system of real animals.
And you also have your own podcast, right?
Yes, I have a podcast called Unsupervised Thinking that talks about this intersection between neuroscience and artificial intelligence and the field of computational neuroscience, which a lot of people haven't heard of.
But that podcast is on hiatus, I hear.
Yes, the podcast is on hiatus for now as I finish writing a book that I'm writing, which is also about the field of computational neuroscience, because many people don't know about it. So it's a popular science book that explains the history of how people have used mathematics and other ideas from physics and computer science to try to understand the brain.
Do you want to give an outlook when it's supposed to come out or not yet? I don't know at what stage you are, to be honest.
Yeah.
I don't know if these are inappropriate questions.
No. It's never inappropriate to ask someone who's writing a book about their book. We're supposed to talk about it. So the writing stage is winding down a bit. That's why I had to put the podcast on hiatus, because I'm getting close to the deadline. I think the anticipated publication date is about a year from now.
So what's the title?
It's called Models of the Mind.
This conversation was recorded on February 21st, 2020, so exactly 6 months prior to the release of the episode. Usually I plan my recording seasons in a way that my guests don't have to wait this long for the release. But it's 2020, so nothing is normal. But this means we'll have to wait for the book not too much longer, and I'm looking forward to it very much. Now, why would I invite a computational neuroscientist to talk about artificial intelligence? Because I think they approach the same problem, how intelligence works, from a different perspective than AI researchers. The field of artificial intelligence wants to create machines that can perform tasks which we think require a certain level of cognitive ability. They do this by implementing computational algorithms. In computational neuroscience, on the other hand, they study a system that already performs cognitive tasks successfully. Experimentalists record data of neural activity, and computational neuroscientists try to use these data to describe the function of neurons using math, and recreate the function of these neurons in computational models.
So you might have, as the input to the model, an image which has pixel values, and those pixel values are kind of analogous to the cones in the retina, because there's 3 different types of cones in the retina that are responsive to 3 different colors, red, green, and blue, roughly. And then you have that in the pixel values, and so that's kind of the start of the model, is maybe you're starting with an image, and then you ask, okay, how does the brain process this image? Well, it has neurons that get input that combine the different pixel values in different ways, and that makes them respond to different things. And so basically you're just chaining together what you think is happening in the real brain, but instead of making, a model made out of real neurons, you're making it out of mathematical neurons, which are just equations that describe what you think real neurons do. So it's just at every point in building a model, you take what you think is happening in the physical thing, find a way to describe it in math, and just kind of chain it all together and see if, the thing that happens in your model matches the thing that happens in the brain.
Probably the biggest research endeavor in the world concerning computational neuroscience is the Human Brain Project, which is a flagship project of the European Union. One of its aims is to create a complete computational model of a human brain. One of the ideas in TechMark's Life 3.0 was that human-like AI could emerge from such a model.
I would say that the approach of the Human Brain Project, which, as I said, is to look very kind of fine-grained at the data, like they're looking at the kind of molecular and cellular properties of neurons and the details of their connectivity and all of that. I don't think that's the most direct route to mimicking human intelligence, because there's a lot of details in the human brain that you can look at. You can spend lifetimes kind of counting ion channels and all these things on neurons and really getting into the details of their structure and all this kind of stuff. Whereas it's not, we don't know if that's necessary for mimicking human intelligence. And so there are just kind of, especially at present, more direct routes for exploring what is necessary to get a computational model to perform an actual task, like show any kind of intelligence. And, the model that the Human Brain Project has built thus far isn't meant to be doing any very interesting computations. It's meant to put together all of this fine-grained experimental data. So yeah, I would say if there is a desire or a concern, I guess, about building human intelligence, that probably there are more direct routes that exist now than trying to capture every single detail.
Okay, so having a computer calculate every molecule in a human brain doesn't sound so feasible. But what about not simulating the behavior of the molecules, but that of whole neurons instead? In fact, the technology that has led to the latest advances in AI is called artificial neural network, or in its large-scale version, deep neural network, as in deep learning. So that sounds like neuroscience has had a major impact on AI already.
It does. It's complicated because the origin of neural networks is in neuroscience, as their names would suggest, because the kind of original artificial neural networks there was a pair of scientists called McCulloch and Pitts that are kind of credited with the first artificial neuron, and they very explicitly base it off of the neurobiology that was known at the time, which was very simple of what was known at the time, and also they simplified it even further to make it into a model that they could think of computationally. So it's basically the idea of an artificial neuron is just a thing that gets in inputs, and you get a few numbers as inputs, you multiply each of those numbers by a different number, which we call a weight, and then you sum it up. And then if that sum is greater than some amount, your artificial neuron is on. And if it's less than some amount, then your artificial neuron is off. And then that artificial neuron can be an input to another artificial neuron, and you do the whole process over again. That's like the gist of what a real neuron is, but it's very simplified for a lot of different reasons. So it is the case that that's what artificial neurons of today and deep neural networks are built on. They have a lot of these artificial neural units that are all connected and have, the tricky part is figuring out what the weights between them should be.
Mm-hmm.
Some people say that this like is too abstract and simplified to really even count as inspiration from the brain. But technically the historical record is such that they were inspired by the brain. So I think it's safe to describe them as such, personally.
But you don't think that they will lead to what do they call it, generalized artificial intelligence or something like that?
Yeah, or artificial general intelligence, AGI sometimes. I think that they are doing a lot right now. These networks are able to perform tasks that we couldn't get computers to perform by any other means, and I don't think that that should be downplayed. I don't know. I mean, people generally, I think, have different definitions of what artificial general intelligence is. For me, it's just the idea of a single artificial agent that can perform at human levels for many different tasks, basically like a mimic of a human, in the sense that, you can make a sandwich as well as read a book or write a book, or, just kind of the whole diversity of human intelligence in one agent is something that could be called AGI in my mind. And yeah, I don't know what it will take to get there. I can see why people are excited now because of the successes of deep learning, that, if we just keep pushing in this direction, that we'll get there. And maybe that's true. It also depends on what pushing in this direction means. So,
as Grace explained, the concept of neurons as it is implemented in artificial neural networks is very derived. Just as neurons in animals, artificial neurons receive an input from one or several sources, perform a computation, and send the result to other neurons. And each neuron can change how strongly it responds to different inputs. In a process called learning, the artificial neural network adjusts the weights each neuron gives each of its input to optimize the result of the output of the whole network. But this is only a mere toy model of what would happen in the nervous system of an animal. While each artificial neuron is the same as the others, evolution and development predetermine a lot of the function of each neuron by its structure and connectivity before learning even occurs.
At least on the neuroscience side of things, that's a kind of very hot topic in some circles. Basically, yeah, how much can we think of as being determined by genes before you even do what we would traditionally call learning? It is the case in the artificial intelligence side that when a network has to learn to, say, identify objects in an image, it needs to basically recapitulate both evolution and development, because it starts really from nothing. I mean, there's some priors that get put in based on the architecture of the neural network. So basically, you could, like in the most unconstrained case, you could just say, I have 100 million artificial neural units, and I'm just going to let them figure out how to connect with each other. But that's not really what people do. They divide them into layers, and they put particular restrictions on what kind of neurons could connect to which other ones, and that helps guide the learning process so that it doesn't have to pick from this completely unconstrained space of how the neurons should be connected. There are some constraints that help it, and how you choose those constraints is dependent on what kind of task you're trying to solve. So there are some ways in which we kind of give it hints or help that maybe humans get through evolution, but there's still a lot of just really from scratch learning that has to happen. And that's not, in some ways that's not fair to the network that it has to learn all of that. Whereas we come built with certain priors, or even if you just think about, the video game example, most humans, if they sit down to play Atari, even if they've never played it before, even if they've never seen an Atari machine or seen anyone play it, they still might understand that, like, oh, this little, like, triangular moving thing is a spaceship, and when I press this button, it shoots things, and, oh, those guys are probably the bad guys, and I should try to shoot those guys before they shoot me. Like, there are just a bunch of built-in concepts that you can already have that you bring to the table, and these models have to learn them completely from scratch.
But these concepts, they are also learned, aren't they? I mean, so that's another unfair thing, I guess, that we ask neural networks or artificial intelligence to reach adult human cognitive ability within months, whereas it takes us like, I don't know, 25 years to have a mature adult brain, right?
Yeah. So that's part of it. So yeah, there's a question of what is truly genetically predetermined and what happens through the course of development. But regardless, all of these things, usually if you're comparing humans to these models, you're probably comparing an adult human on some task. People they try to see like how well can humans classify images if they're presented to them very quickly or if they're very noisy or something like that, and they compare humans to these models. And it's a bit of an unfair comparison in the sense that humans maybe had a leg up in the training process. Now, at the same time, these models are trained on that task and only that task, which maybe makes them, good at it in a way that a human who has to do a bunch of different things couldn't be. But yeah, it's definitely an issue to think about when we think about what we should be giving these networks to help them or to make them more human-like, if that's the goal.
Just as an aside, artificial neural networks aren't the only AI technology. It's just the one that has been particularly successful in recent times thanks to innovation in handling large amounts of data and computing hardware. But will neural networks be the path to human-like artificial intelligence?
I kind of think both. I mean, as I said, the brain is made up of neurons, and it does what it does at some level because of the connections that exist between the neurons. There's details that I'm ignoring that could be relevant. But at some broad level, that's where it gets a lot of its power from. So in theory, we should be able to build artificial neural networks that can do everything the brain does. The complication is how, I think. I think the complication is how more than can we actually do that, because I do think that the brain is doing it. So yeah, the question of training these networks in the right way or giving them, ideas or built-in priors that come from what we think is useful to them, that might be necessary. But in theory it should work. But then also engineering is different than science. And if the goal is to build AGI...
AGI is artificial generalized intelligence, the ability to learn and perform multiple tasks on human performance level, and possibly the ability to transfer skills to new tasks, instead of being only able to do one task.
If the goal is to build AGI and somehow you can get there faster not using artificial neural networks, I don't know what you would use, but if you can, then that's what people will do. That's what the people in AI will do. The people in neuroscience will keep trying to build models that look like the brain because that's what we're interested in.
Right.
So yeah, it's almost a question of just what path will people push hardest on, combined with what's actually going to be possible as an answer that will determine what happens.
Grace and I did not discuss them, but there are interesting hardware developments coming up to support artificial neural networks in particular, so-called neuromorphic processors. Supposedly, they deliver biology-like computing. Another upcoming innovation in hardware, which we didn't talk about at all, is quantum computing. Certainly, this new way of computing could give rise to a type of artificial intelligence that is completely different from our brain-inspired approaches. Alright, so we talked about the bottom-up approach of reconstructing brain function in silico, in the computer, from molecular level details. And we've been talking about how artificial neural networks are inspired by the brain. I think this is a good moment to talk about another sci-fi concept that was mentioned in Live 3.0, uploading of the mind. Now, a brain is not a piece of hardware with memory, an operating system, and software installed. It's all hardware, or wetware, if you're familiar with that term. All memory and computation is implemented in the anatomy of neurons and their connections. For example, memories are stored as subtle changes to the function of many neurons that were activated by the experience that created the memory. These neurons are distributed across the brain, and the changes depend on the specific configuration of billions of cells in the individual brain. That's why you can't upload the mind into a computer. Instead, you would need to scan the brain for every minute detail of the physical and biochemical properties of every single cell and translate it into a computational simulation. Could that work?
I think it like my instinct is that it wouldn't, because I just feel like there'd be so many technical problems that it wouldn't be possible. But in theory, if you really could know everything about a particular human brain, then you should be able to replicate it in silico and it should work the same way. I mean, that's almost what it would mean to know everything about it, is that you know enough to replicate it entirely. So yes, theoretically, this should be trivial. It's just the actual ability to gather all the information that you would need seems so impossible that, that's what we're struggling with at this time. Neuroscience is trying to learn about brains, and it's hard. It's hard to get all the data that you need to know what you want to know.
Uploading a mind in the science fiction sense will probably not work in any foreseeable future. But there might be a workaround if you are looking for a different kind of immortality.
People, in some sense, are kind of low-dimensional. Like, you probably don't need every bit of data about your brain to recreate what, like, most people would consider your personality. Like, I've thought about this in terms of the podcast that I have and the fact that there's a lot of audio of me talking. And, like, could I train a network to just produce me talking about neuroscience and it would roughly, like, match me? And then when I die, like, people can just listen to it. So, yeah, I think there's probably even faster ways for uploading, depending on what part of uploading is relevant to you.
Right. So, well, but that would be simulating and not emulating.
Yes,
right?
I guess.
This is the difference,
yeah,
right?
Yeah.
So that reminds me also of a Black Mirror episode. I think, what was... Oh, yeah, right. The husband died, and the widow gets a service that allows to take all the data that is available about her husband and create an artificial intelligence that simulates him.
It seems possible.
So yeah, that seems to be the same idea.
Yeah,
right?
Especially now that so much of what we do is saved digitally. So many of our conversations are actually recorded and in a format that could be easily analyzed. It seems like you could probably have a decent approximation to a person if you had enough of their data, without their brain even.
With this kind of simulation, we'd approach the idea of transferring a personality into a computer using high-level data. In short, personality is to brain activity what climate is to weather. But would simulating the behavior of a person, instead of emulating the person's brain on a computer, create a conscious human-like artificial intelligence? Most people would probably say this wouldn't count. It did make for a very creepy Black Mirror episode, though.
Yes, yeah. Depends on if you want to live forever for the sake of other people, for them to enjoy you, or if you want to keep experiencing things. But then that gets into whole tricky questions of if, your brain was simulated on a computer, would it be you and what would it experience and stuff?
Another question I have is, why would we even try building an artificial intelligence that replicates human thinking? The whole point of creating tools is to improve our own performance. It's not an exercise in how close we can get to what we consider gods would be like. But human-like intelligence would have the same flaws our own thinking has. Recent research showed that artificial neural networks can be fooled by the same optical illusions that humans are fooled by. What's that good for? Wouldn't we want them not to fall for the same illusions?
I broadly agree. I don't think that the best thing for humanity is replicating humans in silico or human-type intelligence with all its flaws. We have very easy ways of making humans. We don't need fake humans. We would want AI to be better than us in the tasks that we're interested in it performing. And I think the idea of kind of this association or assumption that artificial intelligence would be the same as human intelligence is actually what makes people scared of it, because they think, oh, well, you're going to have a super powerful computer. What if it wants to rebel against humans? But it's like, where do you get the idea that it would want to rebel? Like, that's a human thing. That's a human, like, sense of, not liking being not the one in control and having fear over like what's going to happen to you that would lead people to rebel. We don't have to build AI that has a desire to rebel built into it. I don't think we have to. I don't think that's going to be necessary for it to have the other behaviors that we want. The optical illusion thing, probably largely it is the case that we don't need like to have all the flaws of a human visual system, but at the same time, just generally, it's impossible, I think, to do everything perfectly. So if the network is going to be good at analyzing the world as it normally is, it's probably going to fall for some really weird corner cases. Those like drawings that people do with chalk on the sidewalk that if you look at them from one angle, they look like they're three-dimensional things sitting on the sidewalk. That's designed to trick people because of how light normally behaves. And so sometimes you can't get like there are problems that a system can't solve if it's going to work well in many different scenarios. There's going to be some where it's not going to work well. But generally, yeah, I don't think that we should be aiming to mimic kind of the emotional and irrational elements of human intelligence if we can avoid them at all.
So that's the question, right? Can we avoid that? If we use neural networks to recreate something that is human level intelligent, will then not things like a mind and things like the will to rebel emerge?
I don't logically see why these things have to be related. There's a lot of things that people lump together basically because humans have all of them. So things like intelligence and consciousness and emotions and, like drives, certain types of maybe negative drives and behaviors. And, I can see how sometimes it's not clear that these things can be separated because we look at humans and animals and they do just seem to occur together naturally. But conceptually, they, I think, are separable. I can imagine a thing being intelligent without it experiencing pain. I think that's conceptually separable. Mm-hmm. So I think, it's an empirical question maybe of, in practice, how much we can separate certain things more in the direction of, like if you are creating an artificial agent where you give it some goals and some desires because you want it to act on its own without you having to tell it every little thing to do, how do you balance that with it getting kind of misaligned with what you want from it? That seems like a real question, but the general sense of anything that humans have, something that's equally intelligent will have to also have, I think that that's probably not true.
But you did say that they learn through reward, and being happy about getting rewards is an emotion, right?
Well, so being happy, but getting a reward and changing the weights in your neural network as a result of it is not an emotion. I don't think.
But that's your so what I'm trying to get at is that the function of the emotion in humans is that you want to do more of that. And the function of the reward in the machine is that it wants to do more of that.
Yes.
Right?
Yeah.
So isn't that the beginning of putting emotions into machines?
I think that we use the term reward because we understand it, and this style of learning in artificial neural networks comes from the history of psychology and conditioning studies like Pavlov's dogs and stuff like that. So it has this tie-in to what we as humans who feel emotions call reward. And so you might associate with something like happiness. You could probably come up with a different name for it. And it would mean that the network is still trying to get more of that thing. It's trying to maximize its reward. But if we called it something else, it might not seem so closely associated with emotion and negative drive. Because if we define its reward to be exclusively things that we want to happen in the world, then it won't have a desire to do things that we don't want to happen. So engineering the reward function is a legitimate technical challenge so that it only wants to do things that we want it to do. But the very fact that it has a drive to have reward doesn't mean that it will start to want things that we didn't tell it to want.
And now, artificial intelligence and the singularity. Some people are afraid that by giving AI the task to improve itself and the hardware it runs on, we'd create a sort of positive feedback effect where AI creates better AI, which creates yet better AI quicker, and so on. Such a system, in principle, would create a runaway expansion of artificial intelligence in a historical instance. AI, conscious or not, could become too intelligent for humans to control. Should we be concerned?
I think that there are people who are working on that as a goal, not a concern. Again, if it's getting better and better at something we want it to do, then that's great. Like, imagine applying that argument to like, oh, well, we're going to have an AI that can diagnose and treat illness and like find cures for new diseases. And then, then are you upset that it gets runaway intelligent, or is that awesome?
Well, if that's all it does,
yeah,
yes.
Yeah.
But if you have an artificial intelligence that is designed to create artificial intelligence,
yeah,
then you may have unintended consequences, right?
Yeah, any kind of feedback-driven process can have unintended consequences because it just needs to be slightly misaligned in the beginning, and then it'll just go off in a direction that ends up being, very different from what you intended. So I think the alignment issue is a real one, but just the general notion of something getting better at something that we've asked it to get good at, that seems great. So yeah, but we have to be careful about alignment and about how much power we would actually give any of these systems to do something that we obviously don't want them to do. If we have something that we say, okay, make drugs to cure diseases, and it says I'd like to launch an atomic bomb, I think we can safely say, like, I don't think that's part of your process. I don't think you need to do that. So there should be kind of straightforward ways to put hard limits on these.
Okay, so you're not as concerned about things like runaway intelligence and singularities and things like that.
I'm more concerned that someone whose values are not aligned with mine will have access to these things, and the machine itself will successfully do what it is programmed to do, but the human will program it to do something that I think is bad. That's more the concern. The intents of the humans who wield these weapons.
Mm-hmm. So you think they're weapons?
I guess they can be in the right hands. They're tools, and people use tools for many different things.
You also said the C word already, consciousness. Something that I'm on the fence about consciousness. I don't even know if it's a real thing anymore. So, what is your take on it? So, as a computational neuroscientist.
I guess I assume my take is slightly influenced by being a computational neuroscience, but I think it is real. It's almost the only thing that I'm certain of is that I'm conscious.
Oh, wow.
Yeah, I don't know what else to be certain of because everything else that I've learned has been through my own consciousness. So, yeah, so I think it... At this moment, the interesting bits of consciousness, like how and why it exists at all, can't really be studied through neuroscience. We can study the neural correlates of consciousness, by which we mean if we ask someone, if they saw something, we can study what neurons in their brain have to be active for them to see a thing versus just barely not see it. And, so we're studying their conscious report of what's happened to them, basically, and relating that to neural activity. And I think that's an interesting area. For my PhD, I did a project on visual attention, and that's for a lot of people very closely related to consciousness because when you pay attention to something, it like enters your consciousness in a way that it might not have done otherwise. So I think that those questions can be studied in neuroscience, but the very notion that it is like something to be me, and I don't think it's like anything to be a rock, that difference, I don't know how we tackle scientifically in this moment. I'm hoping that, in the future, this will look like a silly time period where we were confused about something that's not that confusing. But right now I'm confused about it.
Yeah, that's exactly what I'm thinking, that people will realize at some point, oh, it's actually, if we just tweak our understanding of what consciousness is, then we understand how it emerges.
Yeah. But it's like, if you look in the history of neuroscience, there was a time where people thought that the thing that animates nerves, which we now know is electricity and chemical messages, they thought that was not going to be explainable, that it was a vital life force that would never be reducible to scientific inquiry. And you look at that and you're like, why? Why did you think that? Like, just try, and then you'll get it. So maybe that's what's happening with consciousness now, but I'm too stuck in this time period to see it.
Yeah, I have an actually, maybe I'm allowed to say that, an idea about what consciousness really is. And it's basically based on evolution. So you have a simple thing that can move around, and then it has like a simple uh, input output function to control its movement. And then it becomes more complex, and then you have an additional function that is on top of it. So you have a control thing on the basal function, input output. And then it becomes more complex, and then you have yet another system on top of that, and yet another system on top of that. And there is simply, you reach that one point at which you have a layer that is aware. So each level is aware of the underlying level and what is happening there. And you just get to some level at which it is aware of its emotions, it's aware of its sensory input, and it's aware of its thought processes, because it's on top, a level on top, basically. And that's consciousness for me. That's how I understand consciousness.
Do you have a way for testing if a given individual or artificial intelligence has this? Like, what would you look at the architecture of what's driving it, or would you be able to tell by behavior? Because that's always the fundamental issue for me. If you can't measure it, you can't study it.
No, I think it's kind of like emotion. It's an experience. Consciousness. I think consciousness is the experience of having this layer that is aware of all these different processes.
Yeah. But you couldn't tell if someone else was having that experience, because it's like,
no,
just an experience.
They can only tell me that they're having that experience.
Yeah, that's the tricky bit.
Yeah. So that's how I understand it. Or that's my working model for consciousness.
Sure, yeah.
And people want it to be more, and I'm not so sure.
Oh yeah, no, that seems like plenty to me.
Well, people seem to think that there should be something special and not just the next layer.
Oh.
Because my model basically also means that there could be another layer.
Yeah. Oh yeah.
Where you become yet more conscious of all the things that you are not aware. Right?
Yeah,
so right now we're shifting our awareness around all the time, right?
Yeah.
What if there's a next level where you don't have to do that anymore and you're aware of everything that is happening in your brain?
Yeah, that's hard to relate to, but I guess it's theoretically possible.
Yeah. So that's what I think would be the next evolutionary step. But
yeah. See, this is the problem where we only have...
This is sci-fi.
Yeah. But this is the problem when you only have like humans as the example. Then you think, oh, is this all that this could be? Or is this just one example of what this is? I think it happens with intelligence too.
So this was the neuroscience view on artificial intelligence. I hope we were able to convey how certain hyped ideas about artificial intelligence will probably remain science fiction. And I'd like to leave the final words to Dr. Grace Lindsay.
In terms of what computational neuroscience is and the role it plays in all of this, I would say that basically there are people who are trying to understand the brain mathematically, and sometimes that can be helpful for artificial intelligence. But it doesn't necessarily have to be, because it's not the goal, because the goal for neuroscience is to understand the brain. But I think just by having a community that is versed in the quantitative and computational side as well as the biology, it's just kind of an interesting intersection. And some people will kind of play both sides. Like sometimes they'll be doing it for the sake of understanding the brain, and sometimes they'll apply it to try to make artificial intelligence. So it's kind of a bit of an overlapping Venn diagram of what people do. But yeah, I just think that it's an interesting field to exist, especially at this time where you have people who are pretty interested in AI who maybe don't know much about the brain, and knowing that there's a community of people that for some time now have kind of been thinking along computational and quantitative terms about the brain.
What do you think? Will AI be the end of civilization? Or will it simply be a great tool that will help us solve the biggest issues of the 21st century? Send me your answers or questions, comments, or suggestions to info@scienceforprogress.eu or contact me on Twitter @sciforprogress. You'll find the links, resources, and a summary of this episode in the show notes. I thank you very much for listening. Have a good day. Bye-bye.
Goodbye.